Okay, sorry. I think did not realize that the stream has just started. So good evening, everybody, and welcome to the live session for this week. Let me just make sure that I'm also watching it on YouTube. So those who are watching on YouTube, welcome to the stream and feel free to post your questions in the YouTube chat. I think I'll try to monitor that the best I can. And what I also want to do is yeah, so I guess let me just start off by saying that I think the logistics of the last three assignments, I think there was probably a little bit of a misunderstanding, and that was mostly at my end. So I'm sorry about that. I think we will have an announcement very soon, hopefully by tomorrow. So the last 3 weeks have a common theme, and that theme is dynamic programming. How many of you who are attending this call have seen the videos for week 10, which is an introduction to dynamic programming? Can you give me a +1 in the chat if you have already seen the videos from week 10? And give me a -1 if you have not seen them yet. Okay, thanks, Devansh. What about the others? Just give me a quick +or -1, depending on whether you have watched videos from week 10. Okay. Oh, okay. You're quite new, so you haven't done. Okay, so then welcome in that case, Suryam, to the course. I guess Avalok, I hope I'm pronouncing your name right. You have watched the videos from week 10, so thank you for that. Let me just take stock of what's going on YouTube. All right. Hi, Mohit, and good evening, Ahmed. All right, so thanks for your responses, everyone. It looks like the week 10 videos have not been watched by a majority of the current audience. So that's cool. I think it may be a little bit boring if you have seen them. My plan was to sort of get everybody a little bit up to speed on dynamic programming as a sort of a concept. And there's a really nice contest on @Coder called the Educational DP Contest. So this sort of walks you through a lot of different DP problems. So just posted a link to the contest in the chat on Zoom. Hi Mohit, good evening. So I guess I cannot post this link on YouTube, but if you just search for @Coder DP contest, then you should you should get the link to the contest. It has I think 26, like it has a different problem for every letter of the alphabet. And that's really great practice for DP. So in fact, in week 10, I think one of the problems that we do is actually from this contest. I could try to go over that again, or maybe we could just pick a slightly different problem to work with as well. So let me just spend a moment here. Actually, before we do that, let me see if I can show you a different example, just to, because I just realized that what I had planned may not be completely appropriate if you have not seen the week 10 videos yet. So let me see if I can find a different problem to get started with. I'll try to share my slides here in a second. Just give me. All right, sorry about that, guys. Can you Can you see my screen with the bumblebee picture? Okay, awesome. Thanks. Thanks. All right. So here's a puzzle that I think motivates a lot of what recursive thinking and what DP is often all about. So let's try to go through this question as some sort of a warm up, and then maybe we can actually get to a question on one of these contest platforms where maybe we can also write some code and so on, right? Okay. So we have a bumblebee, and you can see this honeycomb structure, this picture in the bottom left corner of the screen. So the bee wants to get from its starting point, which is the cell which is on the first row, the top row, and the leftmost cell. It wants to go from there to the target cell, which is the colored one, which is on the bottom row, and it's the rightmost cell. Okay. Now, the movement of the bee is restricted to neighboring cells. So two cells are neighboring if they share an edge. Okay. So for example, these two cells would be neighboring and these two would be neighboring. But the first cell is not neighboring to any of the other ones. Okay. So in the first step, the bee can only move to one of these two sort of marked cells. Okay. It can also only move towards the right. So for example, if the bee is here currently, let's say the fourth cell in the top row, can somebody tell me if the bee can move to this cell, which is the third cell in the bottom row? What do you think? Would that be permitted or would that not be permitted? Yes or no? All right, no. Thanks, Devansh. Indeed, this cell is to the left of the cell on the top. So this move would not be permitted. You can only move rightwards. So yeah, Tejas, that's correct. It's not permitted. So even though the two cells are neighboring, the move may not always be valid. So the move must only take you forward towards the right. So the question is, in how many ways can you reach the last cell? Okay. And if you're seeing this for the first time and if you've not seen a similar problem before, this can seem a bit daunting because it seems like there could be many different permutations and combinations of ways that the bee could move, right? And so how do you kind of capture all of them? And what we want to do is we kind of want to see if there is a simple way of approaching this question, okay? And let's just do a few examples again to get the hang of it. And again, if you're someone who kind of has already seen this and this is not new for you, my apologies, but I thought this would be like a fun question to sort of start with. So okay, so let me just label these cells here a little bit. So yeah, I guess we could assume that we are indexing 1. So are the labels visible? Yeah, 1, 2, 3, 4, 5, and A, B, C, D, E, F. Yeah. Can somebody please quickly confirm that you can see the labels on your screen? Okay, great. Thanks, Surya. Cool. So in how many ways from the starting point can you get to the cell that is labeled A? It's the first question. I would like to pull up the YouTube thing so I can sort of keep track. Just give me one moment, guys. Let me pull it up to a separate screen or something. Okay, so I hope the screen share is visible again. So, okay, labels are visible. Thanks. So, sorry, people who are watching on YouTube, I was not able to see that screen until now, but now I think I can follow the chat here as well. Great. So the number of ways of getting to the cell that is labeled A. So on Zoom, they were just pointing out that it is 1. And why is it 1? Well, that's because it's a neighboring cell, so you can go directly for sure. The other way may have been to go to the cell that is labeled 1 and then come down to A, but that's not feasible. And the reason for that not being feasible is that it's a leftward move, so that is kind of not allowed, right? So so hopefully we all agree that the number of ways of getting to the cell that is labeled A is 1. Okay, so let me just write that down in red over here. I don't know if the size of this annotation can be increased or not, but just going to say 1. All right. So now what about the cell that is labeled 1? In how many ways can you reach that cell? 2. Okay, you can do that by direct examination because you can go via A or you can come directly. So that would be 2. And for now, because these are small examples, this is okay. We can just do this by inspection. We cannot keep doing it by inspection forever because then there will be too many cases. But just to get some practice, let's ask ourselves, in how many ways can you reach the cell labeled B? That's the second cell on the bottom row. So to everybody who's watching on YouTube, I'm sorry, I think there is a bit of a lag, usually a few seconds. So I think you get to hear the question only about 30 seconds after I have said it. So I may have moved on before you have a chance to reply. So I'm really sorry about that. In case you are on Discord, and you are participating in the course formally, then I think you should have access to the Zoom meeting as well. So feel free to join on Zoom so you can participate more in real time. Okay, so for B it is 3 and Suryam is saying it's 2. So let's okay, so let's think. If we just try to work it out manually, right, by hand, like we did for 1 and A, then we can probably see that you can go via 1. That's clear. You can go first to the cell labeled 1 and then B. You can come via A, right? So that would be another way, right? So you can also go, okay, so let's see, physically I can see 3 options. As I think Devansh was saying it's 3. Prayag is also saying it's 3. So okay, if I just try to spell out the paths, I would say you can go from the starting position. So let me call that 0. So you can, okay, so Devansh has enumerated them. So thanks for that. I was just going to write it out. So you can do 0, 1B, you can do 0AB, but you can also do 0, 1AB. Okay, so that is actually 0, 1AB nahi hoga. It won't be 0, 1AB because 1 to A is a left move. Can you fix that last one, Devansh? It'll be 0, A, 1B, right? Yeah. Sorry, I didn't mean to type that. I think it'll be 0, A, 1B. Exactly. So thanks. Perfect. So those are the 3 ways of getting to B. Now, the question that I want to ask, which is kind of key to understanding, how DP sort of works at large, would be, can you think of, how you got to 3, not in terms of just, kind of enumerating by trial and error all of these paths, but can you think of it in terms of something that you have already seen before, that is already on your screen? So you can think of 3, and let me give you a hint. So 3 is also 2 plus 1. Can you say that like more in words, right? I mean, is there a way that you can interpret this answer in terms of answers that you have already seen? I hope that sort of question makes sense. Yeah, so Devansh is saying sum of the left two adjacent. Exactly, right? So, yeah, Prayag, number of ways to get to A plus the number of ways to get to 1. That's exactly right. So how can you reach B? Okay, or any cell for that matter. How can you reach any cell? Well, you can come via the two neighboring cells that are to its left, because I mean, if there are two cells to its left, for some cells, there will only be one cell to its left, which is fine. So, but the point is that you have to come via a neighboring cell that is to your left, correct? Now for B, the two cells, there happen to be two cells that are both neighboring to it as well as to its left, because left se आओगे तो right move होगा, right? So, you know, you have to come in from a cell to your left. So for B, there are two such cells. And the point is that you have already figured out in how many ways you can get to those cells. You know that the number of ways you can reach A is 1, the number of ways you can reach 1 is 2. So the number of ways you can reach B is the sum of these two numbers, because, you know, every pathway to B is either via A or via 1. There is no other way to reach B, right? And since you already know in how many ways you can get to A and how many ways you can get to 1, you can simply add up those numbers. So for sure, the number of ways of getting to B is at least the sum, because, you know, you can get, you know, you can just come to A in so many ways, you can come to 1 in so many ways. And for each of those ways, you just tag one more step in front of it and you get a different way of getting to B every time. And notice that there are no other ways of reaching B, because every path to B must pass through 1 or A. These are like bottlenecks because of the rules of the game. This is it. There is nothing more to count. So your count is everything that you have counted is a valid count, and there is nothing more to count. So this is the this is, and yeah, right. And in fact, this must remind you of the Fibonacci sequence, as folks are pointing out in the chat, Devansh and Prayag. So it's just the sum of the previous two numbers. And now I think this is probably straightforward. You have to so for 2, for instance, you can come to 2 from 1. And you can come to 2 from B. I think I may have said earlier that there may be cells where you have only one left neighbor. I think this is only the case for the cell A, which has only one left neighbor. So that's what's happening in the base case, so to speak. It's happening in the beginning. But otherwise, if you look at any cell, it will have the cell on either. So the cell on its own row and to the left, and the cell on the other row, which is to the left, these will both be left neighbors. So for 2, it is B and 1. So the number of ways will be 5. And you will see the Fibonacci numbers sort of come up here. For C, it is 2 and B. So it's going to be 8 and so on and so forth. Okay. So for 3, you can come via C or you can come via 2. So that's going to be 13. Yes. My math, like certainly my arithmetic, is a bit rusty, so please let me know if there's a mistake. These numbers look familiar, so I'm hoping that I'm not making mistakes, but let me know if, you know. So the answer is in fact 144. So I hope that, you know, that makes sense. Yeah. Right. So a lot of people have caught on to the fact that this is exactly the Fibonacci recurrence. Now, if you have to implement something like this, then of course you can implement it. So maybe let me see if I can just open Replit here. So let me just say a couple of things, quick things about implementation. Just make a Python Replit here. Can you see my Replit screen, people? Oh, unfortunately, I have to figure out a way of clearing the annotations. Yeah, hopefully they're gone. Let's see. Yeah. All right. For those who are tuned in, I would, yeah, I think from YouTube, it's clear that my screen's visible and you can see code. I mean, there's no code written yet, but, you know, hopefully this is fine. All right. So, So the definition of Fibonacci is kind of naturally recursive. So let's write something like fib of n, right? And what do we want to do? If n is 1, so let's say that's the number of ways. So that's the first number that we want to compute. So that was the number of ways of reaching the cell on the bottom row that was leftmost. So we want to return 1. If n equals 2, then return 2. Remember, there were 2 ways of doing that. Else return, and what should I write here? Return what? Somebody want to help me out? Exactly. So thank you. I will just copy paste that from the chat. And I'm not sure which, let's just print everything. Should probably be. Okay. So I think we went as far as the 11th Fibonacci number in that example. So just for the sake of it, this looks okay. If I had just said range of 12, what do you think will happen? Remember, in Python, range of 12 will be like, sorry, this is mixing up C++ syntax here. This will be I0, 1, 2. Sorry, I think I have a keyboard shortcut that's messing things up a bit. Okay, any predictions? What will happen if I run this code? Range of 12. I starting from 0. Yeah, infinite recursion, exactly. So when you plug in I equal to 0, it does, these cases will not trigger, you know? And now you get fib of -1 plus fib of -2. And, then it's just a downward spiral from there. To resolve fib of -1, the call will be to -1. And that will call -2, and -2 will call -3. And there is nothing to cut off this, recursion, these calls, right? So you have to be a bit careful about things like this. The base cases in recursion is super important. Okay, so you have to be, you have to make sure that your recursion is actually getting cut off, and it has a reason to stop. That is one aspect of it. And of course, the other aspect is, what's the time complexity? What is the running time? So if you had to take a guess, what do you think? Like, how expensive is it to run this function that we are running? Is it polynomial or is it exponential? What would you guess? All right, so I guess you folks already realized that this is exponential. Prayag, you're saying that it's polynomial. Let's see. All right, so let's take a look here. This is this is the code on Python tutor. That's hopefully visible, and you can see that it's going to take 115 steps. And as you run through the code, you will see that is a fair amount of. Oh, okay. Did I actually not correct it? Sorry. I think that's just Python tutor being smart about cutting off the recursion here. You may have actually, I'm sorry. Yeah. So Python tutor does detect that you may have infinite recursion. Let's go back and fix this code. I did not realize that I put in the, yeah, okay. So even for this, it says this exceeds 1,000 steps. If you were to actually run this code, you will see that there are a lot of function invocations that are being repeated as you go along. So for instance, when you're computing fib of 4, you end up computing fib of 3 and fib of 2. But then when you're computing fib of 3, you're computing fib of 2 again. And now when you called fib of 4, there was also a computation for fib of 2. So if you actually try to, walk through this code yourself, you will see that there is a lot of redundancy that's happening in the execution of this code. And one of the things you want to do, like so Prayag was saying it's polynomial, we do want this to be polynomial. And you can sort of fix that by trying to take advantage, leveraging things that you have already computed so that, you don't compute them again, okay? So let's see if there is a different way that we can write this. So one way is to take advantage of just remembering the things, that you have computed. So let's see if we can do that in a reasonable way, okay? So, so with Python, I think one easy way to do this is to just store all the numbers as we go along. So I'm going to describe what is usually called bottom-up DP. You can also do this so-called top-down savings, where you just keep the recursive form of the function call, but just commit these values to memory. And when you invoke the function call, you first check, like, do we already have this value in memory? If yes, then directly return without invoking any recursion. Okay, so just this simple if statement right at the start of the function definition is going to save you tons and tons of computation, and it's going to actually bring down the running time from exponential to polynomial. So this is something that's, I think, described. And also what I'm going to say now is also there in the week 10 video, so feel free to take a look at that when you go back, because I think we actually draw out the recursion tree and explain it in a little more detail. But for now, let's just take a quick look, at how you might want to do this in a way that's evidently more efficient. Okay, so let's initialize. I'm going to forget about this function for now. Initialize a list with. So what I want is fib of I is the I plus 1th Fibonacci number. That's just because of zero-based indexing. Okay, so for example, fib of 0 is equal to 1, which is f of 1. And fib of 1 is 2, which is f of 2. Okay. Okay, so depending on where you're reading about Fibonacci numbers, the sequences may not always start like that, but that's, we'll just live with that for now. Now, so suppose I want to compute, so now I need to populate the list from 2 onwards. In fact, actually it doesn't matter. So let's just say that I want to add 10 more numbers to my list of Fibonacci numbers. Okay, so I should just add to this list. What should I add? What should I append to this list? What do you think I should write here? It's very similar to something that we have seen before. Okay, so let me just copy this from the Zoom chat, or I could copy it also from the function definition that we have before from here. But I don't want it to be exactly this, because these are function calls. That's not what I want. So what I want is so what I want is I want to just add up the previous 2 elements in my list. And that's a huge difference, because I'm not asking the function to actually compute these numbers again. I'm just saying, look at these memory locations and pull up these 2 numbers. So that these are, this with the square brackets, these are 2 constant time operations, whereas these are not constant time operations. That's the amount of time that you need to actually compute the n-1th and the n-2th Fibonacci numbers. Okay, so yeah, no, actually, I think you're right, Devansh. That's actually more or less what I've written, except instead of I and I plus 1, you want to look at things, that you have sort of already computed. So, so I guess I should fix the indexing here. So we should in fact start from 2, so that it makes sense to say 2 minus 1 and 2 minus 2. That will go to the indices 0 and 1. And yeah, I mean, if I want, I guess, if I want to add 10 numbers to my list, then I will just increase that range a little bit. I might be off by 1, but let's. So I think I should rename the function because it's going to be a bit weird to have the same name for the list and the function. So we're not invoking the function in this code anymore. Let's take a look at what happens. So notice that you do get the Fibonacci numbers again as expected, but the number of the number of steps that's taken by this piece of code is going to be, if you were to execute it on Python tutor, notice that you are done in just 23 steps, which is not surprising at all. This is pretty much linear time. You just need as much time as you need to go through the entire array. That's kind of about it. You don't, don't really need anything more than that. Okay. So, the number of times that this for loop runs is proportional to n, which is, if you want to compute the nth Fibonacci number, you need to go all the way till, from 2 to n plus 2 or whatever. So that's n iterations. And for each iteration, it's just 2 lookups. Okay, so that's a constant amount of time. 2 lookups, 1 addition, and 1 commit to memory step, which is the append step. So the plus, the lookups, and the append, these are all constant time operations. So this is really just order of n. So give me a +1 if this explanation made sense and if you appreciate why this implementation, even though it looks very similar to what we did before, this implementation is actually dramatically different from the recursive function implementation. Give me a +1 if that makes sense, and then we'll move on to maybe discussing a different problem. Cool. Thanks, Prayag. Anyone else who can confirm that this made sense? Or if you have a question, then we can talk about that. Let me know if you have a question. Remember when I wrote the recursive version for even a smaller number of Fibonacci numbers, it kind of exceeded the recursion limit on Python tutor. So it was more than 1,000 steps. And so you can see that this is a dramatic improvement. Yeah. Okay, those who are watching on YouTube, can you give me a +1 if you're with me so far and if this is making sense? All right, thanks, Devansh. Let me stop the screen share for a minute so I can kind of pull up a problem that we can discuss. Okay, I don't see any questions on either Zoom or on YouTube, so I think that's permission for me to move on. So let me talk about one of these problems on the @coder DP contest. Yeah. So, so this turns out to be a classical DP, question, something that you would find in a textbook. So in fact, let me know if is anybody here already familiar with the longest common subsequence problem? Give me like a +1 if you've seen this before and you would be bored if I told you about it. If not, I think it's a great, it's a fun problem to sort of practice. But if someone's already seen this, then we'll pick up a different problem from the list. You know. Okay, so seemingly no complaints so far. So let me just maybe tell you about the problem. Okay, so what you're given as input here is two strings, S and D, and there is no promise that the strings are of the same length or anything like that. But you are told that the lengths of the strings are like at most 3,000 each. Okay. Um, so what you want is you want to find out what subsequence is common to both strings. Okay. And among all such subsequences, you want to return one that is as long as it can be. Okay, so let's maybe look at a couple of these examples. Okay, so maybe you had a chance to look at the answer on the previous screen, but what, given these two strings, what would you think is, what is an example of a common subsequence, first of all? So I hope you, the word subsequence makes sense. It's essentially, so a substring would be something like, you know, if you're given a string, let me maybe at least explain the difference between, um, so let's say this is a string, single string, maybe I typed too much. Let me just fix that. So here's a string, right? A subsequence would be any contiguous, a substring would be any contiguous sort of substring. So something like this would be a substring. Okay, so that's essentially you're identifying two indices. Let's say, so let's say that the string locations are indexed from 1 to n. So you want to find two indices, I and j, between 1 and n. Let's say I is less than or equal to j. So you start from the ith position and go till the jth position. That would be a substring. Okay, so it's kind of a contiguous part of the original string. Okay. On the other hand, a subsequence uh, would be anything that's well, I mean, let me highlight an example that will hopefully become clear. So this would be an example of a subsequence. Okay, so these can be broken, like these can be fragments, but you do want that it, you know, you can find it in the string in that relative order. It's just that it doesn't have to be contiguous. Okay, so you know, so for example, jk and kj are both substrings. Jk kj is also a substring, but what is not a substring is, for example, you know, if I were to say something like um, so this is not a subsequence, I'm reasonably sure. I typed out the string completely at random, but I think that's not a subsequence. This string that I'm writing here in blue, this is not a subsequence of this long string at the bottom, because, you know, I can find a D, I can find a K, can find another K, but I cannot find any more. Okay, so it's not a subsequence. So is the notion of a substring subsequence clear? Do we are we on the same page? Okay, just to be sure, give me a +1 in the chat on YouTube and Zoom if you're following so far. Yeah, All right. Thanks. Thanks, Devansh. If you're not following, you probably have a question. So feel free to share. If I'm not being clear about something, it might help other people also if you have a clarification. Yeah. Okay, so now that we understand subsequences, we can talk about common subsequences. So for instance, here, uh, AB would be a common subsequence. It's a string which is a subsequence of both the strings. Okay, so I'm going to highlight that in purple here for you. So would you agree that it's a common subsequence? AB is a common subsequence of both these strings. Is it the longest possible common subsequence? Yes or no? Okay, thanks, Prathamesh. All right, not the longest. And you can find, okay, so maybe we can add X to the mix here. That would also qualify. Now, is that the longest subsequence? Okay, so A by B also. So you could do AXB or A by B, but I don't think there's a way of doing both because the relative order of X and Y is different, in both these strings. So you can also do A by B for sure. What color this is? Okay, fair enough. So there are two longest common subsequences here. We're not interested in how many common subsequences are there, but we do want to output one of the one of the longest common subsequences. So I think here both answers would be considered valid. Yeah, for example, there's in fact a note here which says the answer is AXB or A by B, either will be accepted. So so as long as you get one of them, A longest common subsequence, it should be fine. Okay, so now yeah, you can probably check that the sample inputs make sense. But in the interest of time, I want to talk about a solution. So suppose you have, hypothetically, these are some two strings, okay? And I want to understand, as I said, they may not be the same length. So let's say the ones on top here, which, oh, okay. I don't think I'm able to get to. So let's say that the green boxes are the string S and the gray boxes are the string T. Okay. And remember, just like we had for the B, we wanted to know, in how many ways the B can reach the last location. And we understood it in terms of how the B can reach its neighboring locations, right? So this is a very common theme. We want to understand the final answer in terms of things that we already know. So for us, what is the final answer? It's the longest common subsequence of the strings S and T, okay? Let me ask about a simple case. So let us say that so let's say Q. So let's say that both these strings have Q at the last position. Yeah. So both S and T have the same character in the last position. Okay. And suppose we know um, so let me just introduce a little bit of notation. Okay. So let S be a string of length n and let T be a string of length m. Okay, so n and m. Okay, I hope I just got a notice saying that you can now see my screen. I hope that the screen was visible so far. So I want to know what is the longest common subsequence between S and T, the full strings. And suppose somebody has told me what is the longest common subsequence between the strings, up to the first n minus 1 and up to the first m minus 1 positions. Okay, so suppose I know this information. So suppose somebody has told me that this answer is 4. Okay, assume that you know this. I don't know how you know this, but let us assume that this information has been magically given to us. If we know this, and further, if we are lucky, I will hopefully understand why this is a lucky case later. So suppose we know that the last character happens to match. Then just based on what is in the screen right now, can you tell me what is the longest common subsequence of S and T? If you get this, I think like Deepika Fanda, at least philosophy will be, I think, kind of clear. 5. Yeah, okay, exactly, right. And why is it 5? Because you take that longest common subsequence up to the n minus 1 and m minus 1th character and just add q to it, right? And you will get a subsequence of length 5 for sure. Why can't it be more than 5? Can somebody explain कि 5 से ज़्यादा क्यों नहीं हो सकता? It could have been 6. Could it have been 6? Okay. Right. So the string ended and we can check further. There cannot be more than one common character by increasing the length of the strings by just 1. So that's kind of exactly the spirit of the argument. So one way that I would say it is that, here's a way of saying it, and I'll write it as we sort of go along. So suppose LCS of S and T was 6, then take that solution and remove q from it. So let that solution, let that common subsequence z, let that common subsequence be something that we call z, right? And, if z ends on q, then remove q to get a string of length 5. If it doesn't contain q, then just use z, right? Right? So either z minus q or z itself is a common subsequence of length 5 or length 6 for S and T up to n minus 1 or m minus 1. But we are assuming that when you go only up to n minus 1 and m minus 1, the longest common subsequence that you can get only has length 4. Okay, so if the whole string had a longest common subsequence of length greater than 5, that would contradict this information. Okay, so you cannot do better than 5. Okay, so that gives you sort of one piece of your final answer, one piece of your final solution, and this is how the code will almost look. So if s of n equals t of n, then LCS of this thing is actually going to be equal to this plus 1. Okay. However, Now suppose that you don't have this information. So else. Okay. So this may not be the case always. The last thing may not be common, right? Um, then what can you do? What you know is that, the longest common subsequence is not going to end at the last character for sure, right? Um, hey, Prakhar, hi. So I think at the start of this session, I just mentioned, and I think I've responded to your question on YouTube as well. I think there was a bit of a misunderstanding about how the last three assignments were to be done. So please watch out for an announcement by tomorrow. There's going to be a combined, all the last 3 weeks assignments will be released with a common deadline. And, hopefully, we've just pushed out some questions to the practice section because I realized that it was a bit delayed. So we've just made it a little bit shorter, and you can still do the other questions for practice. We've made it a bit shorter so that hopefully you'll have enough time to do it. So I hope that answers your question, Prakhar. All right, thank you. And thanks for your patience as well. Okay, so now let's come back to this. So if we don't have a match, so let's say one of these characters is Q, the other one is P, so there is no match, then what can we say? Well, suppose I tell you what is the longest common subsequence. Okay, so suppose I tell you what these two quantities are. Okay, so what is the longest common subsequence between all of the first string and the second string up to the last but one character, and the first string up to the last but one character and all of the second string? Okay, suppose I give you these two pieces of information. Okay, so in this example, let's say this was 7 and this was, I don't know if we have that many characters. Oh, sorry, maybe this is a bit ambitious. So let's say this was 3 and this was 4. Okay. Based on these two pieces of information, can you tell me what this answer should be? Just think about it a bit. All right, so Devansh is saying max, so it should be 4. So certainly, whatever substring was a substring of, these two is also a substring of S and T. So whatever is a substring of these two is also a substring of S and T. So again, itna to hai. I mean, we know that the longest common substring of S and T is at least 4 in this example for sure, because you can just take whatever substring is witnessing these numbers. So somebody has told you this is 4. You ask them, okay, how is it 4? What was that substring? And they tell you, okay, AXCQ is a substring of length 4 for S up to the last but one position and all of T. But then this is also a substring of S and T, so no problem, right? So definitely, our answer is at least 3 and it's at least 4. And since we want to maximize, we will take the maximum of these two numbers. So we know that, this is something that we can surely produce. Can we do better? Is there, can we be sure that this is in fact the longest common subsequence? You cannot have something that is more than 4. So suppose, for the sake of contradiction, suppose the longest common subsequence was 5. Does that contradict these two pieces of information? Just give me like a quick yes or no. Do you think that if the longest common subsequence of S and T was 5, then that contradicts the two pieces of information that are written in purple? Yes or no? Okay. You think it does not contradict? Okay, so Prathamesh is saying it does contradict. Okay, so let's think about it. So suppose the LCS of the complete strings S and T was 5. That means that there is some common subsequence of length 5. So let's highlight it. Okay. So this common. 5 थोड़ा बड़ा number ले लिया, so just give me 1 minute, guys. I'm also a bit OCD about getting the color right, so it's going to be a bit slow. Should be able to do it. So let's say ये last वाला भी involved था. Okay, first tell me, can the longest common subsequence look like this? In this case, where we have said that S of n is not equal to T of m. Else का मतलब S of n and T of m are not the same. So remember this. So can the longest common subsequence of length 5 be in those highlighted boxes? Is that possible? So I'm claiming, okay, no. And okay, so hopefully that is clear. Ki that cannot be. And, and the reason for that is we know that these two last dibbas are not the same, right? So the longest common subsequence will at best involve one of these two dibbas. It cannot involve both. Okay, so we agree on that. Right? So let's say it involves this. Okay, but if this is indeed a common subsequence, then what statement does it contradict? अगर ऐसा है तो फिर, how is the LCS of S of 1 to n and T of 1 to m minus 1, 3? Is this a problem? So notice that if the longest common subsequence looks like this, right, then this is also a common subsequence of S of 1 to n and T of 1 to m minus 1. But somebody has told you that the longest you can manage with those two strings is just 3. So do you agree that this is a contradiction? So Devansh, Prayag, is this making sense? Yeah, this is a contradiction. Great. Yeah, thanks. So this cannot be, right? And if it was some other situation, mando ki this was like, you can take any situation. You want to say maybe the longest common subsequence looks like this. Tab to aur bhi, matlab, it will contradict both of these pieces of information because this is the longest common subsequence for both. But if it was, something like this, then this contradicts the other piece of information. Ki between 1 to n minus 1 and 1 to m, the longest you could have managed was 4. But abhi to, I'm seeing 5. So that's a contradiction. So, of course, the main thing is it's important to remember that the last two pieces are not the same. Because if the last two pieces were the same, then, then you won't be able to get this argument. So hopefully that is clear. So, so basically, so what you said about the max of these two quantities, the true answer cannot in fact exceed the max. Okay, so the max is achievable and it is the best that you can hope for. Both of these pieces of facts are important to be able to write your code like this and be sure that it is correct. Okay, so now let me, I realize that it's getting a bit late, so let me just maybe begin to wrap up a little bit here. But here basically what you can say is that this is the max of LCS of 1 to n minus 1, T of 1 to m, and LCS of 1 to n, LCS of S of 1 to n and T of 1 to n minus 1. So my original plan was to also walk you through this code, but really this is the heart of it. If and else, and of course you have to, put it inside a loop, etc., etc. But basically this is the idea. So what you're going to have is, this is essentially the recursion. You have to be careful about your base cases. So, and yeah, you have to, well, if you have strings of length, actually a simple base case would simply be to return 0 when the strings are of length 0. So kahin na kahin n minus 1 karte karte these numbers will become 0. So if any one of them becomes 0, then you return 0, because with an empty string and any other string, the longest common subsequence simply has value 0. So that's an easy base case to code. And so when you write your, this is the entire recursion really. So you look at S and T, you look at the last characters. If they are the same, then it is 1 plus reduce both n and m by 1. If the last two characters are not the same, then reduce one at a time, invoke the recursion, and pull out the better of the two values. Okay. And so that's essentially what you do. What I want you to think about a little bit is, again, the implementation. If you implement it directly as a recursive function like we did for Fibonacci, you will have, pretty high complexity. So the event time complexity is exactly what I was going to say, is something that you can think about offline. But if you just imagine, imagine as that you're storing these things, right? So like in Fibonacci, it was just one straight array, right? Here, it's not exactly one straight array, because, you have these numbers sort of I and J, right? In some sense, you're kind of trying to figure this out for, all of these pairs of indices, so to speak, because it's possible that when you are trying to compute, let's say, the LCS up to these, well, let's say up to, the point is that, okay, I'm just trying to drive some intuition for the fact that this may be a combination of n and m, and it's actually a good thing to just think through what the table looks like and what is the time complexity. But one thing that you want to keep in mind is that these things are just free lookups. Okay, you are not actually invoking. So when you implement the DP in a bottom-up fashion, you're just storing these values. So every time you call these functions, these are not really function calls. You're just looking up the values from a table. So I think my bracketing is a bit off here. So let me fix that. So I'll take the max of these two things. So think of these as just being, simple lookups, and then think about, what is the sort of the time complexity. It's, I think, a fun, sort of a fun thing to work through. So for any given value, it's really a constant amount of computation, because, this if else checking is constant. And then you just have table lookups, taking max and storing this value, right? So, okay, so the best case minimum of n and m, I'm not sure about okay, so the best case would be when, let's say, both these strings are the same, or one string is a substring of the other, for example. Yeah, so it can be as fast as that, I guess. So for example, if both strings are the same, then the if statement keeps getting executed and you finish off, I think, you finish off in linear time. I think that kind of makes sense. Yeah. We also want to think about what is the worst case complexity, right? And also think a little bit about, either a top-down or a bottom-up implementation. Either way should be fine. I think it's a good exercise, to actually implement it. It's problem F in the AtCoder problem set. So please do try it out. The reason I'm not going to get into a complete discussion of the running time, at least maybe we can pick it up in the next session, is because it's getting a bit late and I wanted to just make one more point. And that last point I want to make is the fact that you are not just looking to output the value of the longest common subsequence. What this will give you is the length of the longest common subsequence. But remember, what you want to output here is actually the sequence, not just the length. Okay. So in DP, the DP table typically gives you the value of the solution, does not give you the solution itself, usually. Okay. So to actually figure out what a solution is, you have to do something called backtracking, which is to say that you go back to the DP and ask it, what choices did you make and why? Okay. So when it made this choice, implicitly it was adding the last character of both the strings to the solution. And then it was saying, okay, then I will hand it over to the recursion angel who will tell me what to do by magic. Okay. But then what is the recursion angel doing? Well, it's just digging further down and asking this question again and again. So every time you do a +1, you're actually adding one letter to the answer. Okay. And that's kind of what is happening. So you can think about actually, in fact, next time we can do this, we can look at a Python or C++ implementation of this DP and actually run it through some examples to see how the DP is making choices, and then write some code to actually backtrack and produce the string. That's a fun exercise to do. If anybody wants to do it sooner, just tag me on Discord, and maybe we can try to do it sooner over an informal session before next week's live session. Otherwise, we will pick it up next Saturday. But now we are well over the hour, and it's late evening, so you're probably getting ready for dinner or something like that. So let me not delay everybody here. This was a lot of fun to do, and special thanks to everyone who sat through this and was so interactive. That was very helpful for me. So thanks for the discussion, everyone, and thanks for joining, everybody. So let's call this a wrap about here. And I look forward to seeing you back next week. And I have not been as active on Discord as I would like to, so I'm trying to fix that now. So feel free to tag me, and I think I will, I'll try to respond quickly, and we can continue this discussion over there as well. In the meantime, the AdCoder DP problem set is a great one. So if you want to, especially if you're getting started with DP, it's a great place to start your practice. So thanks a lot. And Prakhar, we can talk about that in the next session. But basically, assume you're talking about the exam. The format is very similar to the assignments. In fact, many questions are from the assignments, maybe with the numbers changed or whatever. Of course, that's probably about, that's some part of the paper is like that. And the other parts are just new questions, but in the same style, in the same format. And we have tried to distribute it equally over all topics. So I hope that helps. But we can, if you have any specific questions, we can talk about that next time. Yeah. All right. So shout out to Prayag and Devansh. Thanks so much for the interaction throughout, and everyone else who joined. So really appreciate it. Good night for now, and let's catch up next week. So thanks, folks. Bye bye. Mr. Karthik, if you are around, we can close this session as well as the live stream. Thank you.